In this video, you'll learn how to build and run an industrial AI agent locally on your edge device using Python, LangChain, Ollama, and the Mistral large language model. I'll start by walking you through an AI agent that relies on Claude, a cloud-based LLM from Anthropic. Then I'll show you how to swap out the agent's brain with the fully local LLM running on your machine using Ollama. My name is Kudzai Teresa, and I regularly publish tutorials on industrial data and AI right on this channel. So if you're new here, be sure to subscribe so you don't miss any upcoming videos. This is part 2 of a 5-part series on how to build agentic AI for industrial systems. If you're jumping in fresh with this video, don't worry, I'll give you all the context you need to follow along. All the code used in this tutorial is available on GitHub. You'll find the link in the description below. Okay, so let me quickly describe what we're working with. I have an industrial AI agent that monitors a simulated batch production facility. This agent connects to real-time equipment data through an OPC UA server endpoint where it checks the material levels in our storage tanks and verifies the availability of our production machines. It also connects to our plant database to check how much raw material is needed to produce a batch of any given product type. Using all this information together, it provides detailed data-driven responses to questions like, can we produce 50 batches of product A? And it doesn't just give you a yes or no answer, it explains why, showing you the calculations and the reasoning behind its decision. Now let's take a look at our existing AI agent code. So here is our current setup. I have 2 Python scripts that handle our data access. The first one reads data from an OPC UA server, getting real-time information about tank levels and machine states. The second one reads data from a timescale DB database, pulling product recipes and material requirements. And then I have a tools Python program that takes these 2 scripts and uses the LangChain framework to transform them into tools that the LLM can call whenever it needs to retrieve data. This is the bridge between our AI agent and our industrial systems. And then finally, I have the main Python program where everything comes together. Let me walk you through the key components here. First, I'm importing all the necessary components. I'm using base model from Pydantic to define our output structure, ensuring we get consistent structured responses. I'm using chat Anthropic from LangChain Anthropic for our LLM, which is currently Claude. And I'm importing various prompt and parsing utilities from LangChain that help manage the interaction. The critical imports here are the tool calling agent from LangChain.agents, which gives us an agent with the built-in ability to call our tools, and the agent executor, which actually executes the functions. Next, you can see where I define exactly how I want my output structured using Pydantic. I want a clear decision, either yes or no. I want detailed reasoning that explains that decision. I want the actual material availability data and machine states. And then I create an instance of chat Anthropic with a specific Claude model that I want to use, which is one of the things we are going to eliminate in this video. Now, the really important part is the prompt template. This is where we give the agent its instructions. We tell it exactly what its job is, which is to determine if we can complete a production run. We explain what tools it has available and what each one does. We specify the format we want for the output, and we include any special rules or edge cases it should handle. After setting up the prompt, I put all our tools into an array and create the actual tool calling agent, passing in the LLM, the prompt, and the tools. And then I wrap it in an agent executor, which is responsible for actually running the functions. So let me run this code quickly to show you our agent in action before we modify the code. Okay, so you can see here it has returned, yes, production is possible. And then it gives us the reasoning. For 5 batches of product A, we need material 1, and then it does its calculations. And then it also checks the current availability and matches that. And then here it specifies that we have got sufficient materials. And then it gives me the machine states, material availability, And then it also tells me what tools were used. Okay, so now let's make this work without any cloud dependency. So here's what we're going to do. Instead of using Claude as the LLM, we're going to replace it with a local model that runs entirely on our machine. And the nice part is we're going to reuse our existing code. The data connections stay the same, the tool definitions stay the same, the agentic logic stays the same. We're literally just going to swap out the brain. So how exactly do we run large language models locally? We're going to use a tool called Ollama. Think of Ollama as Docker, but specifically for AI models. It handles all the complexity of running these models, managing resources, and providing APIs. Ollama is completely free and open source, and it runs on Windows, Mac, and Linux. So let's get it installed. Okay, so now that Ollama is installed, we can verify the version. Okay, so Ollama is successfully installed and we're ready to go. Now, the next thing that we need to do is to choose a model to deploy on our hardware using Ollama. So when you go to ollama.com/library, you'll see a comprehensive list of available models. Each model has different characteristics, different sizes, and different capabilities, which obviously means different hardware requirements. Now, the type of hardware you have will dictate which models you can run effectively. In my case, I'm going to download the Mistral 7 billion parameter model. And to do that, I'll go to the terminal and type in the following command. Okay, download is complete. So let us verify if it's working by running Okay, let's just ask a simple question. Okay, so we've got a large language model running entirely on our machine. All right, let's modify our code to use Ollama instead of Claude. First, we need to install LangChain Ollama. And then we import chat Ollama from LangChain Ollama. And then next, we find where we instantiated the Claude model, which is this line here. And then we replace it with the Mistral model. Okay, now we don't need to change our tools, our prompt, or anything else. LangChain abstracts away all the differences between the models. Our agent should work exactly the same way, just with the local LLM instead of a cloud LLM. Okay, so let's run our locally powered agent and see how it performs. Okay, so as you can see, we've managed to actually get a response from Mistral, which basically gives us the output, but it's sort of like struggled with the structuring, which needs to be adapted specifically for Mistral. So as you can see, we've got the reasoning here. To determine if we can proceed with producing 4 pages of product A, let's first gather the necessary information, and then it goes off and does the calculation. And then here it says, the decision, production can proceed. Enough materials are available in tanks 1 and 3, and all machines in the batch plant are operational. Sufficient materials equals to true, and then it gives the machine states. Now, while the AI agent we just built is fully functional and runs locally at the edge, there's still a major limitation. It only reasons over structured data, real-time signals from our OPC UA server, and product recipes from the timescale DB database. But what about unstructured data like maintenance records, PDFs, or Excel spreadsheets that often contain critical operational context? For example, imagine there's a scheduled maintenance task due in 8 hours. If our AI agent doesn't know about it, it might make the wrong call about whether to proceed with production or not. So in part 3, I'll show you how to build an agentic RAG pipeline so your AI agent can bring unstructured document into its context and make more smarter, more informed decisions.